Hello, everyone. I am here today to talk to you about conservation of energy. Hopefully, by now, you have done the notes for day 1 and day 2. So, just to kind of recap very briefly, we are going to be discussing energy in 2 main forms in this particular chapter. We have potential energy, which is affected by the mass of the object, the Earth's gravitational acceleration constant, which is 9.8, and then the height of the object above ground level, or whatever would be considered ground level, or a height of 0 for that object. Then we have kinetic energy, which is basically energy in motion, and this is going to be 1/2 mass times velocity squared. Please make sure that you guys understand that that is not times 2, that is going to be squared as an exponent. So assuming that you have already studied those topics and you have a good grasp of what those 2 types of energies look like individually, then you should be ready to move on to this concept of conservation of energy. So we talked about this briefly in momentum. You guys should have learned the idea of conservation of mass and matter in chemistry. And the main idea here is that whatever it is that we're discussing cannot be created or destroyed. So I know that we reviewed this earlier before spring break, but I just want to go over it again. The law of conservation of energy, conservation of anything, is neither created nor destroyed. So what does that mean for us in terms of understanding how we are supposed to interpret the questions that we get, and how that shows us or illustrates, or how can we show that energy is conserved? Well, our energy is simply going to get transferred in one form of energy to another. So it says it is just transformed from one form into another. And again, we are going to be focusing on potential and kinetic energy as our forms of energy. So these are 2 types of energies that are conserved. In other words, we're going to find that the energy is going to simply transition back and forth between potential and kinetic. We are going to assume that there is no friction present in these particular types of questions unless the problem tells us differently, okay? So kind of like we did with momentum, we said that once we knew that total amount of energy, it was the same before and after the collision. Well, when we're talking about conservation of energy, the total amount of energy is the same throughout the object's motion and its changes in position or speed or whatever it is experiencing. Anytime you read a question, please understand this. If you read a word problem or a conceptual question and it is asking about energy that is lost, I need you to know that technically there is no such thing as lost energy. But when we're talking about the idea of conservation for our potential and our kinetic energy, it may simply be that the energy has transformed into a different type of energy that is not going to transition back into our kinetic or our potential. So we've discussed before what friction is. It's the rubbing of 2 surfaces against each other. So if you take your hands and you rub them together right now really quickly, you'll notice that your hands get warm. So remember that we've already discussed that friction causes heat. Heat, or thermal energy, is a type of energy that is not going to be returned into my object's speed or into my object's potential height, because once it is transferred into thermal energy, it does not come back into our object's motion, okay? We are going to be referring to the categories of potential and kinetic energy collectively as mechanical energy. So this right here, ME, stands for mechanical. So this says mechanical energy total. In other words, whenever we're talking about the total amount of energy we have, we can also just ask how much mechanical energy is it. What you need to understand is that you're simply adding your 2 categories, potential and kinetic energy. So we're going to look really quickly at this drawing over here. Let's assume that this is an object. You can call it a roller coaster. You can say that it's, I don't know, some kids on a sled at the top of a hill, whatever you want it to be. Let's say that we somehow know the height of our hill And so based off of, let's try that again. Based off of our hill's height, we can say PE equals, oh guys, let me try that, I'm so sorry. We can say that PE equals mass times gravity times height. And if we knew all the values, we could simply calculate that. And let's say that we calculated a value of 50 joules. We are going to say, if you look at this illustration, this is the absolute highest point that my object can possibly achieve. That's really important information. We're also going to say that at this moment, my object currently does not have any velocity. It is initially at rest at the top of the hill. So you can see that we have our kinetic energy value here, but that is in gray, KE for kinetic, and it is gray. It's there because I want you to go ahead and begin understanding that we must always account for both the potential and the kinetic energy of our object. But at this location, the value of our kinetic energy would be 0 joules. Okay, so our object begins to slide down the hill. Now we already understand that as it moves down the hill, it is going to be accelerating. Its speed is going to be increasing. The farther it goes down the hill, the faster it is going. So we can see from this illustration that when we get to this location on our hill, my object no longer has a kinetic energy of 0, but it now has a kinetic energy value of 35 joules. Well, where did that energy come from? It cannot be created or destroyed. Well, no. It had a height of whatever height in meters h, but then obviously now it has some new height, which is less than what it started with. So that means that it has less potential energy than what it started with. So what we would find in our questions is that we would probably get enough information so that we could use this new height right here and calculate the potential energy that my object has. And because my total amount of energy, my mechanical energy, is always going to be PE plus KE, I would simply add these two amounts together to find out how much total energy is available. Well, since I knew up here at the highest point it was all potential and no kinetic, this 50 joules was my total amount of energy available. So when I get here, I still have to have a total of 50 joules. And if the height allows me to calculate how much is potential, then I subtract the 15 from the 50, and I'm left with 35. And so that's how I know how much kinetic energy is available. Okay? When we get down here to the very bottom of the hill, we can see that we now are at ground level. We are the lowest point that we could possibly be. So my potential energy, once again, must be accounted for, but because it's a height of 0, then it is 0 joules of potential energy. So where did all that energy go? Well, my graphic is missing the KE here, sorry about that. And so we are going to say, well, if my total amount of energy has to equal 50 joules, if there's 0 joules of potential energy, then that means all 50 joules must now be in the form of kinetic energy. Okay? So conceptually speaking, we need to understand that my potential energy at the absolute highest point, assuming that my object has 0 kinetic energy there because it has a velocity of 0, that potential energy at the absolute highest point is my total amount of energy. When my object gets to the absolute lowest point, it has lost all of its height, it has lost all of its potential energy. Therefore, all of that energy must have been transferred somewhere. Assuming that we are ignoring friction, then all of the energy must have been transferred into kinetic. So that's why we have a kinetic energy of 50 joules down here at the bottom. This also means this is the moment where my object is moving the fastest, because remember, kinetic energy is based off of the amount of velocity that my object has. The last thing that I want to say here is that we need to understand that this relationship gradually changes from potential to kinetic as my object is moving, but we can also kind of summarize these questions about the highest point and the lowest point if we can just recognize that however much potential energy my object had at the top of the absolute highest possible point it could go, and the amount of kinetic energy my object has at the very bottom, meaning when it has reached ground level or the absolute lowest amount of absolute lowest position it could possibly reach, those two values are equal. It's very clear to see here. Obviously, the questions that you're going to get in the future are going to be a little bit trickier, but if you can understand this concept, then it'll make life a whole lot easier, okay? So we would say that my mass times gravity times height at the top is the same as 1/2 mv squared at the bottom. And so this is a relationship that I typically do not provide for quizzes or tests, but if you understand the concept that the PE at the top is equal to the KE at the bottom, then you should be able to design this formula by yourself. Another way that you can think of it is by taking this main idea that PE plus KE gives me my total energy. We could say PE plus KE initially, or at the top, or in the beginning, when we were doing our momentum, or before equal or after, right? So our PE plus KE before is the same as our PE plus KE after the object has moved, or our initial over here on the right, and then our final over here on the left. If this feels more comfortable because it looks more like the conservation of momentum we did before, great. Here's what I need you to understand. Conceptually, if we are saying that our potential energy is the absolute highest point and we have a kinetic energy of 0, then this whole thing becomes 0. If we understand that our potential energy on the final side is representing that absolute lowest point where we have a height of 0, then our potential energy final is 0. So you see you're left with our initial potential energy is equal to our final potential energy. It's the same relationship. It's just a matter of which version of it you feel more comfortable understanding and then using on your own. Okay, so that's the gist of the concept of conservation of energy, and then I will work some practice problems for you here in just a little bit so that you have some assistance and understanding of how you're supposed to take the information you're given in a word problem and use this knowledge to guide you through the math. Have a good day.